To use a consumer appliance, you expect a simple transaction. You press a button on a remote, and media instantly appears on a screen. A general-purpose PC environment is chaotic. It runs hundreds of background processes, handles unpredictable hardware interrupts, and manages constant thermal fluctuations. For Home Theater PC, or HTPC, to mimic a dedicated DVD player, it has to completely hide this chaos. It relies on the appliance illusion. Creating this illusion requires a rigorously synchronized stack, low-power standby states, strict metadata abstraction, and hardware-level APIs. To understand this architecture, we have to trace a single infrared pulse backward through the entire system. A red pulse hits the receiver, expanding into a sprawling block diagram showing the microcontroller, CPU, OS, and GPU layers. The HTPC architecture is massively scaled up compared to a standard player. Within this, 3 distinct failure domains emerge: MCU, software, and thermal exhaust. If a bottleneck occurs in any one of these 3 domains, the system lags, stutters, or overheats, and the appliance illusion shatters instantly. True hardware simplicity is never natural. It is the result of rigorously engineered abstraction across multiple compute layers. Right before the remote button is pressed, the host PC is sitting dormant in deep sleep, or in S3 standby state. Waking a high-wattage primary CPU just to monitor the room for a background infrared signal burns unnecessary power and generates excess heat. This schematic shows the ARM ATSAM3U1E embedded microcontroller sitting isolated between the active IR receiver and dormant motherboard. Notice the power draw hovering over the MCU. It draws just 1.65 microamps in a backup state, continuously monitoring the IR interrupt line. The millisecond the IR pulse is received, the chip snaps into an active 96 MHz state. A data pathway illuminates, instantly routing the signal to the high-speed USB 2.0 block at 480 megabits per second. Moving this data efficiently requires direct memory access, or DMA. The ATSM3U1E features 17 peripheral DMA controller channels. These allow the microcontroller to pass data directly to system memory without waiting for the main processor to wake up and assign resources. By bypassing the CPU completely, this architecture prevents the thermal spikes that would otherwise trigger cooling fans from a simple keystroke. During this process, the raw analog infrared pulse is converted into a standardized USB human interface device, or HID, command. The embedded microcontroller acts as a critical low-power buffer. It maintains the instant-on response time without incurring the thermal penalty of a running CPU. The HID command leaves the USB bus and is immediately intercepted by the host operating system. From the OS, the command is handed off to the Media Center software environment, such as XBMC or Kodi. When a user presses play, they intend to select a movie. The operating system, however, only understands how to locate and execute an MKV container file. Bridging the gap between human intent and machine execution requires metadata scrapers. On the left, raw directories are parsed using strict naming conventions to query external databases. This pulls down metadata, rendering a polished poster grid on the right. An internal database bridges the visual poster clicked by the user and the exact MKV file path. Thanks to this database structure, the initial remote command is successfully resolved to a specific local file directory. With the file located, the software layer issues the final playback execution command back down to the hardware. The software layer's primary job is not playback. It is translation, converting human intent into exact file directories so the hardware can take over. We now follow that execution command from the software layer down into the hardware processing layer. Here we encounter the final bottleneck of the HTPC, decoding heavy H.264 or VC1 video streams inside a physically confined chassis. This wireframe details the 2003 MSI Mega 651's architecture. Look at the spatial constraints. Installing an AGP video card completely blocks the primary intake fan's airflow. Brute forcing playback on the CPU in this starved environment drove temperature spikes above 63 degrees Celsius. Solving this thermal crisis meant shifting the decoding workload away from the CPU entirely. The solution arrived through the DirectX Video Acceleration API standard, or DXVA2. This diagram shows the DXVA2 logic gate routing the high bitrate data stream away from the struggling CPU, channeling it directly into a high-capacity GPU node. System load drops dramatically. CPU utilization falls from 30% down to 5%, and the temperature stabilizes. GPU hardware acceleration neutralized the thermal crisis of small form factor PCs, allowing high-definition playback to physically exist within an appliance-sized footprint. Stepping back from the thermal layer, we can now view the complete system architecture from top to bottom. We return to that initial infrared remote pulse, now fully contextualized by the underlying stack. In this block diagram, a data packet moves from the IR receiver to the ARM microcontroller. It enters the XBMC software block, transforming into a file path command, then cleanly bypasses the CPU entirely, hitting the DXVA2 GPU node to output video. The embedded microcontroller handles low-level state persistence to provide the instant-on response time. The software database standardizes chaotic file systems to provide the clean, polished interface. And the hardware API offloading defeats physical thermal limits, allowing the entire machine to run quietly inside a living room cabinet. Together, these three optimized layers continuously maintain the appliance illusion. In systems engineering, the most complex architectures are specifically designed to look like they are doing absolutely nothing.